Hello everyone, this is my CA4, an explanation of CA3. First, what is a matrix? Fundamentally, a matrix represents a linear mapping from one vector space to another vector space. It is usually written as a table of numbers. General matrices are the workhorses of mathematics. They can stretch, skew, or rotate the geometric space. Today we focus on a special subclass, the permutation matrix. Unlike general matrices, a permutation matrix is a square matrix where each row and each column contains exactly one entry equals to 1, with all other entries being 0. Its function is pure and simple. It permutes basis vectors without changing their length or angles. Identity matrix is a special type of permutation matrix representing no permutation. Why are these important? General matrices are the standard tool for solving massive systems of linear equations and are the engine of computer graphics, allowing us to project 3D models onto a 2D screen. Permutation matrices, on the other hand, are critical in quantum computing. They represent logic gates that shuffle information without losing data, which is essential for reversible computing and encryption algorithms. To analyze them more deeply, we use a compact notation. Since a permutation matrix is sparse, we can represent it using a simple array or vector. In this format, the number at the ith position indicates the column index of the one in the ith row. For example, the identity matrix is simply written as a natural sequence 1, 2, 3 to n. If we observe the operation in array form, we can find a fascinating rule. The number at position I in the resulting vector is a value retrieved from the index specified by the original number at position I. Then let's consider the equation a1, a2, an times a1, n2, an equals 1, 2, 3, n. To satisfy this equation, ensuring the first position of the result is 1, it must satisfy that if ai equals 1, then it must be that a1 equals I. More generally, as a square root of an identity matrix, this array must satisfy the following necessary and sufficient condition. For any index I and j, if ai equals j, then it must be that aj equals I. We can use a pair of number I, j to represent ai equals j and aj equals I. Therefore, we can generate all square roots of the nth order identity matrix in the following way. For the sequence from 1 to n, we either pair a number with another or leave it unpaired. Each number must participate in at most one pairing. For example, for sequence from 1 to 4, we can pair 1 with 2 and pair 3 with 4, and then we get the matrix 2, 1, 4, 3. And we can also pair 1 with 3 and leave 2 and 4 unpaired, and then we get a matrix 3, 2, 1, 4. In summary, the problem of counting the square roots of an nth order identity matrix reduces to determining the number of ways to pair elements in the sequence from 1 to n, and obviously this is a recursive problem. When n equals 1, there is only one possibility, the unpaired set 1. When n equals 2, there are two possibilities, the unpaired set 1, 2, and the paired set 1, 2. For n is greater than 2, each new number n can either remain unpaired and the other n-1 numbers can be paired freely. This gives us fn-1 possibilities. All n can be paired with any one of the other n-1 numbers, and then the other n-2 numbers can be paired freely. This gives us n-1 times fn-2 possibilities. Finally, we arrived at the beautiful recurrence relation. Let me walk you through the several functions. First, we have the permutation function. This acts as our generator. It uses the standard Python itertools library to create every possible ordering of numbers from 0 to n-1. This gives us the raw data from all possible permutations. Second, create permutation matrix. This function takes a simple permutation list and converts it into a formal n times n matrix. It initializes a matrix of zeros and places a 1 at the specific column index for each row. And then we have permutation matrix. This function simply aggregates the previous steps. It generates the complete group of permutation matrices. For an input n, it returns a list containing all possible matrices. Finally, the core logic resides in enumerate square roots. This function performs a brute force verification. It iterates through every matrix in the group and checks if it's a proper square root. This function uses the dynamic programming method, creating an array f to store the results of each iteration. By applying the formula derived earlier, we calculate the number of square roots for an nth order identity matrix. Finally, since the assignment specifies excluding the identity matrix itself, we must subtract 1 from our final result.